If we scale down the Earth-Sun distance, that's 93 million miles, to just 1 meter, then Alpha Centauri, which is our nearest star system, would be 276 kilometers away. That's 171 miles on this scale. So if Earth and the Sun are right here, next to each other, the next star system is the distance of London to Paris. But remember, that's scaled down. We've compressed the real distances. Now, you've probably heard about Voyager 1. It's our fastest spacecraft ever sent into space. It's been traveling for about 50 years. How fast is it going? About 38,000 miles per hour. That sounds fast, doesn't it? But let me tell you what that means. Voyager 1 is traveling at about 0.006% the speed of light, 0.006 of 1%. At that speed, it would take Voyager 1 about 75,000 years to reach Proxima Centauri. 75,000 years. That's longer than human civilization has existed. So the first thing we have to understand is the distances are incomprehensibly large. Not just big, incomprehensibly large. And this creates our first fundamental problem, which is time. If you want to go somewhere in an unreasonable amount of time, let's say 100 years or even 1,000 years, then you have to go very, very fast. You have to go as a significant fraction of the speed of light, maybe 10% of light speed, maybe 5%. But here's where we hit the next problem, and this is where physics gets really interesting. You see, there's this thing called the rocket equation. It's not complicated, but it has profound implications. The basic idea is this. To accelerate something, you have to push it. You push it by expelling mass behind you. Newton's third law. Every action has an equal and opposite reaction. So if you want to accelerate a spacecraft, you have to throw mass out the back. That mass becomes your propellant, your fuel. Now, here's the problem. The faster you want to go, the more fuel you need to carry. But carrying more fuel means your spacecraft is heavier. And if it's heavier, you need even more fuel to accelerate that extra mass. See, it's a vicious cycle. The relationship is exponential. This isn't some limitation of our current technology that we might overcome. This is a fundamental mathematical property of how rockets work. It's baked right into the equations. Let me give you a specific example. Let's say we want to send a spacecraft to Alpha Centauri, which is our nearest star system, about 4.4 light years away. We want to get there in a reasonable time, say 40 years. That means we need to travel at an average speed of about 10% the speed of light. Now, we also need to slow down when we get there, right? We don't want to just crash into the star system. We want to decelerate. So we really need to be able to accelerate to 10% light speed and then decelerate again at the destination. To do this with nuclear fusion. And fusion is the best we can probably do with physics we understand. The fuel would make up about 95% of the total mass of the spacecraft. 95%. That means only 5% of your spacecraft would be the actual ship. The crew quarters, the life support systems, the instruments, everything else. The rest is fuel. And even with that enormous amount of fuel, we're talking about systems that are almost impossibly complex. But let's think about this differently. Let's say we somehow solved the rocket equation problem. Let's say we invented something magical that let us get around it. What's the next barrier? It's Einstein. And this is where things get really profound. You see, Einstein's theory of special relativity tells us something very important. Nothing with mass can travel at or faster than the speed of light. It's not a speed we haven't reached yet. It's a fundamental law of the universe. As you accelerate an object closer and closer to light speed, its effective mass increases. The energy required to accelerate it further increases without bound. To reach the speed of light would require infinite energy. Infinite energy. That's not something we're going to develop. That's not a problem we're going to solve. It's a statement about how the universe works. So even if we wanted to go faster than 10% the speed of light, say 50%, the energy requirements become absolutely astronomical. We're talking about energies that would exceed the entire energy production of human civilization for many, many years. And as you get closer to light speed, this problem gets exponentially worse. It's not that we don't have the technology. It's that the universe itself has set a speed limit. And approaching that limit requires more and more energy in a way that becomes impractical almost immediately. Now, let's assume, and this is a big assumption, let's assume we somehow overcome these problems. Let's assume we develop some form of nuclear fusion propulsion, or antimatter propulsion, or something we haven't even thought of yet. We've got our spacecraft. It's ready to go. It can travel at, say, 10% the speed of light. The journey to Alpha Centauri will take 40 years. What happens to the people inside this spacecraft over 40 years? This is where biology enters the picture, and it's every bit as challenging as the physics. You're traveling through interstellar space. You're surrounded by cosmic radiation. Now, on Earth, we're protected from this. We have a magnetic field around our planet, the magnetosphere, and we have an atmosphere. These shield us from cosmic radiation. But in interstellar space, there's no protection. There's nothing between you and the relentless barrage of high-energy particles coming from supernovae, from active galactic nuclei, from cosmic rays everywhere. These aren't gentle particles. They're incredibly energetic. They can penetrate materials. They damage DNA. They cause mutations. They increase cancer risk. And we don't currently have a technology to shield against them effectively. You could, in theory, build thicker shielding, heavier materials around the spacecraft. But then you add more mass, which means you need more fuel, which means you need more energy. And we're back to the rocket equation problem. You could use a powerful magnetic field to deflect particles, but generating and maintaining that field requires enormous amounts of energy. Energy that has to come from somewhere. Beyond radiation, there's the physiological effects of prolonged weightlessness. In microgravity, your muscles atrophy. Your bones lose density. The fluid in your body shifts. Your eyes change shape. These aren't minor problems. Over years, over decades, the human body degrades in ways we still don't fully understand. Yes, we have exercise. Astronauts on the International Space Station exercise for hours every day, but they're only up there for about 6 months at a time. We're talking about 40 years, or 100 years, or more. And then there's the psychological challenge. You're in a small enclosed space, with a handful of other people, for 40 years. You can't leave. You can't go outside. You can't go for a walk. You can't see the natural world. You can't experience weather or seasons or the feeling of standing under the open sky. Human psychology isn't equipped for that kind of isolation. We have cases from Antarctic research stations where people spend 8 or 9 months in isolation with a small group. Many of them experience depression, anxiety, personality conflicts. And that's months. We're talking about years. Now, some people have proposed solutions to this. Generation ships, for example. The idea is that the voyage is so long, maybe 170 years to reach a star system, that multiple generations will live and die aboard the ship. The great-great-grandchildren of the original crew members will be the ones who arrive. That's an interesting idea, but it raises enormous problems of its own. First, you need a lot of people on a generation ship to maintain genetic diversity. You need hundreds, maybe thousands of people. That's a massive spacecraft. That's much more mass to accelerate, which means much more fuel, which means much more energy. You're back to the rocket equation problem again. Second, you need to maintain a functioning, stable society over 150 or 200 years. You need governance systems. You need to keep people motivated to take care of the ship when they won't live to see the destination. Psychologically, this is extremely difficult. Historically, human societies haven't been great at thinking and planning across those kinds of timescales. Third, maintaining the ship itself becomes a problem. The spacecraft is a closed ecosystem. Over time, systems fail. Materials degrade. Micrometeoroids puncture hulls. Magnetic fields fluctuate. Computer systems fail, and you can't call a repairman. You have to have people aboard who can build replacement parts from raw materials. You have to grow food. You have to recycle water and air. For 200 years. This is not a small engineering problem. This is perhaps the most complex closed-loop system ever attempted. And we've never done anything like it. We've never maintained a closed ecosystem for more than a few months. Now, another proposal is hibernation. Suspended animation. The idea is that you freeze the crew when they board the spacecraft, and they sleep through the entire journey. When they arrive at the destination, they wake up. This sounds like it solves a lot of problems. You don't need as much food. You don't have the psychological issues. You don't need to maintain a stable society. But we don't actually know how to do this yet. We can freeze cells. We can freeze embryos. But freezing and thawing a whole human body, preserving all the neural connections, all the biological systems, we haven't figured that out. And there are serious questions about whether it's even possible. When you freeze tissue, ice crystals form. They destroy cell membranes. They break DNA. Is it possible to preserve a human body in this way and revive it intact decades or centuries later? We don't know. It might be possible, but it might also be fundamentally impossible due to thermodynamic principles. Let's step back for a moment and think about the destination. We're going to all this trouble, 40 years in space, incredible energy costs, tremendous risk. Where are we going? We're looking for a habitable planet, a world where humans can live. We need liquid water. We need an atmosphere with oxygen. We need a biosphere, or at least the potential for one. We need temperatures in a range that human bodies can survive. Now, we're discovering exoplanets. Thousands of them. But most of them are nothing like Earth. They're too hot, too cold, too close to their star, too far from their star. The conditions are wrong. Some might be in the habitable zone, the region where liquid water could exist, but we know almost nothing about their actual atmospheres or surface conditions. And even if we find a potentially habitable planet orbiting Alpha Centauri, and we spend 40 years getting there, and we arrive and land, we still have to live there. If the planet is a dead world, no life, no atmosphere that we can breathe, we have to terraform it. We have to fundamentally change the planet's atmosphere, its temperature, its water distribution. This is not a project that takes decades. Terraforming would take centuries, thousands of years, and we don't even know if it's possible. We haven't done it anywhere. If the planet already has life on it, if there are organisms, microbes, maybe plants, then we have to worry about pathogens, diseases. Life that evolved on a different world might be incompatible with human biology, or it might be perfectly compatible, and we could catch some disease that kills us. We don't know. This is a genuine danger. Or imagine this. We spend 40 years traveling. We arrive. We land on the planet, and we realize we can't survive there. It's the wrong kind of environment. It's not habitable, and we're stuck. We can't go back. Earth is 40 light years away. Even at 10% light speed, the journey back would take 400 years. Now, I want to address something that people often bring up: advanced technology. Maybe in the future, we'll develop some technology we haven't thought of yet. Maybe we'll invent a warp drive. Maybe we'll find a wormhole. Maybe we'll develop some new form of propulsion that sidesteps these problems. And I'll be honest with you, I'm not going to tell you it's impossible. I learned a long time ago not to say that something is impossible. Science is full of surprises. Maybe there's some physics we don't understand yet. Maybe there's some way to manipulate space-time in ways we haven't imagined. But here's the thing. These aren't just technological challenges anymore. These are challenges built into the structure of the universe itself. General relativity, Einstein's theory of gravity, allows for some theoretical solutions like wormholes or warp drives. But even if those are possible, the energy requirements are absolutely staggering. We're talking about the mass energy equivalent of planets or stars. Energy scales at what physicists call the Planck scale, the fundamental scale of the universe where gravity and quantum mechanics merge. These aren't things that any civilization we can imagine would have access to. You need to be controlling the energy output of stars to make this work. And even then, we're not sure these things are stable. A wormhole might collapse as soon as you try to enter it. So let me ask you this. If interstellar colonization is this difficult, why do we keep talking about it? Why is it such a common theme in science fiction? Why do we dream about it? I think it's because it's a beautiful dream. It speaks to something deep in human nature, the desire to explore, to expand, to find new worlds. And there's nothing wrong with that dream. Dreams are important. They inspire us to develop new technologies. They inspire us to understand the universe better. But I think it's important to be honest about what the actual obstacles are. The problem with interstellar colonization isn't that we lack the will or the imagination or even, necessarily, the technological capability. The problem is that the laws of physics, the fundamental structure of the universe, make it extraordinarily difficult. Not impossible, maybe, but so difficult that it's not a practical goal for humanity, at least not in any timescale that makes sense. Think about it this way. Our entire history, all of recorded human civilization, is only about 5,000 years. We're talking about voyages that would take 100 years, or 1,000 years, or 10,000 years. We're talking about committing resources on scales that are hard to imagine, building spacecraft that would cost more than the GDP of nations, resources that could solve problems here on Earth. And we're doing this to reach places that might not even be habitable when we get there. Now, let me tell you something about the Fermi paradox. You've probably heard of it. The astronomer Enrico Fermi asked, if life is common in the universe, if intelligent life is common, where is everybody? Why haven't we detected signals from alien civilizations? Why haven't we seen evidence of them? One answer, and I think it's a pretty good answer, is that interstellar travel is just this hard. Maybe not for biological creatures, but for anybody. Maybe advanced civilizations also find that the barriers to interstellar colonization are just too great. Maybe the universe is full of intelligent life, but they're all stuck around their own star systems. They can communicate across the galaxy with radio signals traveling at the speed of light, but they can't travel. So they can hear each other, but they can never meet. That would be a kind of cosmic isolation, loneliness on a universal scale. Every civilization alone on their own world, or perhaps throughout their own star system, but never able to reach beyond that. Now, there are people who work on these problems. There are scientists and engineers thinking about how to overcome these challenges. And I respect that work. Some of it is very clever. Some of it is genuinely fascinating. There are proposals for light sails, using beams of energy to push spacecraft to incredible speeds. There are proposals for antimatter propulsion. There are people thinking about the engineering of closed-loop ecosystems. There are people working on cryogenics and hibernation. This is good work. It's intellectually challenging. It pushes the boundaries of what we know and what we can do. But I want to be clear about something. Even if we solved every single one of these technical problems, we still have the fundamental constraints. We still have distance. We still have the speed of light. We still have the energy requirements that scale exponentially. And here's something I want you to think about carefully. Even if interstellar colonization became theoretically possible, would it be wise? Would it be good? We have enormous problems here on Earth. Poverty, disease, environmental degradation, inequality. We have limited resources. We're not sure how much longer our planet can support our current way of life. Are we really going to spend trillions and trillions of dollars, resources that could solve problems here, on a vanishingly small chance of colonizing another star system? Maybe the dream of interstellar colonization is actually holding us back. Maybe it's keeping us from facing the real challenges we have here. Maybe instead of dreaming about spreading humanity across the galaxy, we should be dreaming about how to live sustainably on one beautiful planet. I'm not opposed to space exploration. I think space exploration is wonderful. I think it's important. Studying the universe, understanding the laws of physics, developing new technologies. These are great human endeavors. But let's be honest about what's realistic and what's fantasy. And there's another possibility I want to mention. Maybe we don't need to colonize other planets. Maybe we don't need to spread humanity across the galaxy. Maybe the future of human experience isn't physical exploration at all. Maybe it's virtual. Maybe in the future, consciousness can be uploaded to computers. Maybe we can explore the galaxy through robots and probes, operated by uploaded minds. Maybe we'll become something very different from what we are now. Something that doesn't need to be physical, doesn't need food and air and protection from radiation. I don't know. But if that's possible, then we're not really colonizing stars anymore. We're doing something else entirely. Let me summarize what we've talked about, because I think there are some fundamental points that are worth remembering. First, the distances involved in interstellar travel are almost incomprehensibly large. The nearest star is 4 light years away. That's 6 trillion miles. No matter how fast we go, that's a long journey. Second, to make that journey in a reasonable time, we need to go very fast. But as we approach the speed of light, the energy required increases without bound. This isn't a problem we can engineer around. It's a statement about how the universe works. Third, even if we had unlimited energy, we still have biological and psychological challenges. Long-term exposure to cosmic radiation is dangerous. Prolonged weightlessness damages the human body. Long-term isolation damages the human mind. We don't have solutions for these problems yet. Fourth, we don't know that habitable planets exist around nearby stars. And even if they do, we'd have to land and survive there. We might have to terraform. We might face unknown pathogens. Fifth, the energy cost is almost certainly prohibitive. We're not talking about amounts of energy that a civilization could produce. We're talking about amounts of energy that would be economically absurd, like the entire GDP of human civilization for many, many years. So interstellar colonization is a fantasy. Not because it's impossible. Maybe it's possible, I don't know. But because it's so difficult, so expensive, and so time-consuming that it's not a realistic goal. At least not for us. At least not in the foreseeable future. Now, does that mean we should give up on space? No, not at all. I think we should keep exploring. We should keep developing better spacecraft. We should keep studying exoplanets. We should keep thinking about these problems. But we should do it with our eyes open. We should understand what we're actually facing. And maybe, just maybe, we should focus our energy on the one habitable planet we actually have. We should figure out how to live sustainably here. We should solve the problems we have. And if we do that, if we create a stable, sustainable civilization here on Earth, then maybe in the distant future, thousands of years from now, our descendants, with technology we can't even imagine, might attempt interstellar travel. And maybe they'll succeed. But that's a future project, not something we should be planning for today. You know what I find interesting about all this? I find it interesting that the universe seems designed to keep civilizations isolated. The speed of light is a cosmic speed limit. The distances between stars are vast. The energy required to traverse them is enormous. It's almost as if the universe is trying to keep intelligent civilizations apart, to keep them on their own worlds. I don't know why that would be. It's just an observation, but it's an interesting one. Anyway, I hope this has given you some insight into why interstellar colonization is more difficult than we usually imagine. It's a beautiful dream, but it's a dream that runs up against the hard rocks of physics, biology, and thermodynamics. And that's what science is about, understanding where the real limits are, understanding how the universe actually works, as opposed to how we wish it would work. Thank you for listening.